everyone. So nice to see you all. So this talk will be kind of technical and will cover how we can use the new features in the latest C++ standard. So I put C++20 in the title, but it also covers some elements of 17, but especially those two last standards, and how we can use that to write audio plugins in a declarative way. So declarative is a word that has been already heard in this conference, like for instance, during the talk on functional programming, this kind of thing. And it's a nice property when you want to write some code to write it in a declarative way. It's extremely simple way of laying out code and data. And we'll see how we can right now do this in pure C++ without needing to use any kind of specific library, just by writing simple C++ structs. So I'll start directly with spoilers. What's the takeaway of this talk? This talk mainly talks about reflection in C++. So you may think there is no reflection in C++, and you'll see that actually there is reflection in C++ right now. And reflection-based design enables a lot of things. It enables better reusability of code. It allows to reach no overhead when you want to write a plugin that will be, for instance, made as a VST, as an RTAS, AX, Max, PD object, that kind of thing. And it leads to simpler code. So in exchange, there are some limitations which are due to what is possible right now in C++. And then I encourage you to lobby C++ committees so that we get proper reflection in the language to make everything much simpler and much better. So yeah, current C++20 enable. So I've tried to find correct acronym, but I'm really dissatisfied. So if anyone has a good idea for an acronym after watching this talk, please send me a mail or something, and I'll happily put it somewhere. All right. So what is the motivation for this? So there are a lot of things a lot of properties that we want to achieve in our code. We want to write a code which is as simple as possible, which has no dependencies, does not use any library, that kind of thing. I'll explain why. But first, I'd like to show various examples in the wild of audio plugin frameworks, like things that allow to write some audio code and have it work as a VST, as a VST3, like all these kind of plugin APIs, and what kind of abstractions we have today to bridge our plugins to that. So I hope the code is big enough. So here, for instance, this is a low-pass effect. So if you see your code here, don't worry, it's not an indictment. Like there's just nothing else that could be done at the time. But right now, for instance, we have a plugin framework with, if I can point, yep, no, I can point. Okay, so here you can see that we have parameters, and parameters are input as strings. So this is like super bad. Why is it bad? Because if you have a typo in your string, then the compiler won't scream at you, because the compiler don't know about your strings. It doesn't know that cutoff frequency is actually a variable. And as such, this really reduces code quality, I believe. This makes it easier to make typos that won't be caught by the compiler. And our compilers are super advanced space-tech machinery. And yet, when we do this, we disregard all that, and we just do things at runtime for no good reason, I believe. So that's a first example. Another example of something which is quite common is using enumerations for instance, listing all the parameters, inputs, outputs of a VST plugin or something like that. And it's a tiny bit better, because enumerations, at least if you make a typo, most likely the compiler will complain at you. But still, it's not as simple as just using, for instance, your parameter variables directly in a struct. So that's not as good. And also something that we often find in this kind of frameworks, it's that we have a notion of parameter, and parameter, which is something which has a name, a range, like minimum, maximum, a step, and all these things that mostly are used to display something nice to the user. But it all takes space in every instance of our plugin. So it's definitely not something zero cost. Often it is implemented as like some data object which sits there and takes space for. And the question is, how could we lift this from runtime to compile time instead? How could we put this information of what is a parameter in the type system of C++. So we'll see that there are some C++20 features which allow to do that pretty much entirely. Third example, so it's even worse, well, it's worse in some ways and better in other ways than the previous one. In this one, you'll see that the gain slider is even allocated dynamically. So for one, it's okay, but if you have like 20 or 30 like this, every time you'll try to access your parameters, you'll kill your branch predictor. So, but on the other hand, this one stores a pointer to the floating point value, m gain, and this is a bit better because this means that at least we can lay out our parameter contiguously, which will be better at runtime for cache behavior. But still, that's a lot of complication for just saying that we have a gain, and which is between I don't know 2 and 110, and yeah. Another example, so far this was only audio processors that will work, for instance, as VSTs, but I'm also concerned with things that will work, for instance, as max MSP or pure data objects. And these environments have the particularity that they not only support audio processing, but also message-based processing. That is, you can send a message in the OOP sense to a max or PG object, and they'll interpret it. And here we have a set, for instance, on this library, we have a set of attributes that we can define, a set of messages which will call functions. And the big problem with this is if we want to take this code, for instance, this algorithm, so the actual audio algorithm is just this little part here. And if I want to put it in another environment, then I literally have to rewrite everything because all of this, it's all a big framework which has its own way of specifying parameters, inputs, outputs. And it's definitely like it's some kind of balkanization of audio processors, audio plugins, audio objects. And I think there's no good reason for things to be like for one effect to only work with one framework. And we can find ways to write effects that don't depend on such frameworks. Last example, which gets a bit better, in this one uses more recent techniques. So here we can see that we can put a bit more things in the type system already. So a few properties of the parameter are put as part of the type system, but not all of them. For instance, the name of the parameter is still a value. It will still be stored in the structure. It will still take space. We still inherit from base classes, and you'll see in what I'll show that we don't have to do any kind of inheritance anymore. We can just have members layout in struct and things just work. And but still, we are very close from this in theory. And the last one, just for the log, so this is not even C++, it's C. And in C, what do we have? We have, well, switch and switch cases. So we switch on the number. And so here, if you change something in your spec, you have to make sure that all your indices are correct in all your switches. Don't do this. And to give an example of, for instance, this is one parameter class taken from one of this library. And every instance will have all these members. And if you, for instance, have a max patch with 30 instances of those, then all the instances will have duplicate versions of all this data, while it's actually just static data that is global. It doesn't depend on individual instance. So my experimental observation from all this is that so all these systems mostly use class-based inheritance. They all inherit from some audio objects class processor, which provides virtual methods that you have to implement. And that works if you want to have polymorphism across your organization. That is, if you are like a company who makes audio effects, then you say, okay, everyone in the company inherits from audio object, and well, it will work. But it doesn't work at the scale of the ecosystem, because your organization's requirements, they are maybe not exactly the same that my organization's requirements, and someone will say, okay, but maybe if we pass these parameters in this direction, maybe it'll be 2% faster on RM64 or something like that. And everyone ends up doing their own thing. So my question is, how can we actually allow everyone to do what they want and still don't have to write tons and tons of glue code? And yeah, the big problem is that all these systems, they implement their own custom object-oriented system on top of the C++ object system. And by this, I don't mean the virtual table polymorphism, runtime polymorphism system in C++, but I'm talking about just the basic C model with structs and members and things like that. We already have all the information we need in C structs, and yet, because we don't have reflection, we can't take this information and create plugins from it. Well, actually. So yeah, so just to give a name to this problem, it's called the quadratic glue problem, because we have, on one hand, M system, VST, I don't know, max, etc., etc., n audio algorithms. So, and we have to write M times n glue code, or right now use abstractions like, you know, iPlug, DPF, Juice, and systems that will use custom runtime system on top of the existing runtime system of Max, VST, etc., to bind everything. So the idea is, how can we do this instead of at compile time without using code generator or something like that, just by using raw C++? And yeah, how do we do that? So my pet peeve is rage against the glue. And also the question is, it's of portability, because like if you write, for instance, a Juice processor, then it will only work on platforms that Juice support, which is like a lot of platform, of course. But let's say tomorrow I want to make it run on, let's say, Haiku or Serenity OS or some niche operating system, then I'll have to port the whole of Juice if I want to run my processor. While if my processor was just a simple C++ struct, then it would run from the get-go. So I want to mention Faust and Sol, which are solutions to this problem, which aren't in C++. So I'm interested in C++, and I voted that I liked C++ this morning at the poll. But I mean, the reason is simple. Sometimes you have to do something in C++ that you can do in, say, Faust. Or if you want to call some library in Faust, well, it's hard, or you have to compile your first code C++. So I don't know how you handle this if you want to call some native code. But here, the limitation is with just one C++. Really something you pipe it to GCC, Clang, and it works. So we have to define what is an audio processor. So for this talk, it will be very simple. It's something with inputs, which can be audio inputs, controls. There is a function, and there is some output, which is audio, and maybe some control output, emitters, etc. So the easy part, what we all know to do, is defining the function that takes the inputs and writes the outputs. But what is super hard in C++ is enumerating and declaring the ins and outs, parsing their metadata, what is their name, etc., etc. C++ has historically been bad at that, and we can find like Usenet post from 95 would say, no, we'll never have reflection. It's terrible because they only knew about Java reflection, and of course it's terrible. But now we know that we can have static reflection in C++, so we need it. Yeah, so like I said, yeah, most of the existing solutions are enum-based or X++based. We don't want that anymore. The processor of your processor should be entirely defined through elements that the compiler can type check. Like, there's no reason that we need to write anything more complicated than that to write a game processor. So we can argue that we could write it in functional way with some like just directly out equals in times gain. And that's what we could do. And I think the presentation after mine hints at something like that. So I advise going there too. But in terms of metadata, this ought to be enough. And for instance, if you do some C#, some games with Unity 3D, you know that you can just define a C# object, and Unity will parse your members and just display them in the user interface. It's beautiful. Artists love it. But C++ compilers, right now, they aren't advanced enough to allow defining everything with only the above. Do you know what is missing? Does someone have an idea of what is missing? And what especially in reflection? What can't we reflect here in this? With what? The range of parameters, yes. And here?
If you could turn the fields to a tuple of them and their names.
Yes, their names, especially their names. So, and sadly, my talk doesn't have any solution for the name thing, but everything else we'll see how we can do that at zero cost. So we can get very close thanks to a technique which was implemented in the Boost library called Boost PFR. But so I know that Boost is a scary name. This library actually exists in a standalone fashion, so it's really a header only, very simple, a couple of headers, and it has one limitation, which is aggregate types. So aggregates in C++ are very simple types, stuff that don't have user-defined constructors, things like that. But for what we want to do, it still enables a lot of things. So trade offer. I have a library. It will take a bare C++ struct, and in turn, you'll get VST plugin, ossia API, Python binding, generated UI, pure data object, max object. And I called this library Avendish. And so this is an example for this talk. And I don't want the takeaway of this talk to be use this library. The takeaway is think about the ideas in this library and implement them yourselves, because it can make, I think, the whole ecosystem a bit better. So I'll give some examples of how an object looks. So it's just a bare struct. And in this struct, you have some metadata. So metadata specified really as function that returns strings, things like that. And then you'll say, okay, I have these inputs, and this is just an anonymous structure. And inside we have child structures. And so I will give examples which are very bare, which don't use any library, and then I show a helper library which can be used to simplify the code. But I want to make it clear that no dependency is required. You don't need to inherit from anything. You don't need to just write structs with members, and we'll be able to say, okay, my inputs are A, which is a float, B, which is a float, and a very simple function. So this is an addition. So and here it's the most important thing. Since it's just struct, we can just access the struct members to do our computation. You don't need to go through some random runtime system that you don't have control on. You just have to say, okay, I have my inputs. It's this float, and well. And an interesting thing is that since we don't have inheritance with this, you can't prevent your own code to be consumed by this library. As soon as you have the code which has the right shape, and the right shape can be as simple as an operator, a Lambda, which doesn't take any arguments, then we can do things with it. So it's very unlike inheritance, where everyone has to inherit from a base interface class. Here, everything is defined through the shape of objects. So this is just taking the ideas of Stepanov in generic programming, but applying them to, well, the whole structure, a whole object system. So to give a bit more involved examples, so something where we will have a control, here you just say, okay, my outputs, so here I don't have a specific output, and my input will be a control with a range. We set a min, a max as a const eval structure. So this won't take any space in the structure, of course, at runtime. It's stored somewhere else in your binary. Here, your gain object is just one float. And something interesting that we can do, so with, in particular, C++ concepts help a lot writing this. So it's not something that concept made possible, but it made them simple. And that is, if you look at the previous slide, my computation function, it was an operator which didn't take arguments. And this one is an operator which takes a float as input and outputs a float. So it's something that can be used as a monoprocessor. But as soon as something works as a monoprocessor, we can also use it as a polyphonic processor by instantiating it multiple times, things like that. So, and since we don't inherit from anything, we aren't tied to a particular API style. We can pretty much do what we want as soon as it fits the concepts of, let's say, audio programming, media programming, I don't know how to call that. And I think that, well, what's important is coming up as a community with the good concepts for audio and writing them down and trying to write code that fulfills these concepts. So, of course, I think you're most familiar with this kind of, where are you? This kind of way of writing audio. You take a buffer of channels and another channels input, channels output, number of frames, and you do your processing. So everyone here, I guess, knows this way of writing audio algorithms. And of course, that works too, because, well, what will be the point of making a library when you can't do something as simple as that? And another interesting thing here is that we can, for instance, define our VST programs in terms of our inputs and outputs. So here, say my parameters are this, that, and we can just have a simple structures which will be a copy of the inputs. So of course, it won't fit all use cases. Like you won't make the next reactor or contact like that. But for a lot of simple plugins, I think it can work. And to show an example, so this is the same thing, but with some helper types, which are pretty independent. And I'd say if you want to use this part, you can make your own helper types in-house, and it's fine. And what we can see, which is pretty cool, is that in C++20, we can pass pretty much everything we want in template arguments, so structure, strings, things like that. And that means that all of this is lifted out of the runtime system into the type system and doesn't bear any cost, any particular cost at runtime. The size of this object, low pass, is just the size of the inputs and outputs, and that's like a couple of floats, and that's all. So that's better for your cache, that's better for a lot of things, I believe. And again, you just have to access, for instance, your inputs and outputs directly through these members in your struct, and it does what you expect. So this is the next part of the code. And so yeah, here we take, okay, we go look for the number of channels in our audio input, and well, we just do some computations, simple low pass filter. So yeah. So there were a couple of tentatives to go there. So if you want to go on my GitHub, see the various tries, and I think this one is the last one. So how is the library architected? So there are a few parts which are independent. So the main one is the audio objects, which can be like entirely independent of anything. They can live in their own place, etc. They can use some helpers for simplicity, but it's not mandatory. And they can use C++ concepts to check that they indeed validate the concept of, say, an audio processor, MIDI processor, video at some point, that kind of thing. And then on the other side, we have the bindings which will implement the VST Max APIs by going to check at compile time what are the fields of our objects, things like that, and generating, well, the correct Max API call, listing the right number of parameters in the VST structs, that kind of thing. And in order to make it work with various distinct shapes of objects, for instance, mono objects, stereo objects, then we have some wrappers which will use concepts to overload on what kind of object we do have. And so with these two things, then we can have a fairly wide range, and we can accept a lot of various different kind of objects and make VSTs, etc. of them. So I'll just show a quick example of how does it work to consume the okay. Oh, it doesn't want to be shown. How it works to consume, for instance, such an object. So there is in the repository a simple dump example which just prints all the properties of an object. So it's a few, yeah, for instance, here to print all the inputs, all the parameters. Then we have something which allows to say, okay, for all member in our processor, then we will list, okay, what's its index, what's its name, what kind of control is it, does it have a minimum, maximum, initial value, is it an enum, and if it's an enum, maybe we can print all the enum possibilities. Is it, because yeah, of course, we don't want things to just work with float, we want to be able to use any random kind of data type, which makes sense. And for instance, if I run this example, this will give something like Okay, so this is the dump of an effect, low pass effect, and well, it will just print everything. So that means that, for instance, for getting a JSON out of something, well, you can just do it. And here, this is this low pass thing, and the code of the effect, it doesn't have any dependency. It's just like, it includes the stud vector, but nothing else. And we can still get all these information. There is no weird macro system, no preprocessor. It's just the C++ compiler who does a fairly admirable job, I believe. Okay, so back to the talk. Hey. Okay. Loading. Okay, so now I'll talk a bit about the actual C++ features, because I know you're here for that. So this will only talk about core language features, not standard library, and you have Timur's talk, which was quite nice for that. So we have the main feature is concepts. So it's interesting because concepts isn't something that enables actually new things, like with the substitution failure is not an error techniques. You could do it, but it was such a pain, and you have to write multiple overloads every time to, well, depending on what you want to do. And with concepts, it's very easy to write a function which will do two very different things depending on its template arguments. So, but before getting to concepts, the most important thing, I think, is require expression. That's the big new thing, I believe. And require expression is something that basically is able to say, okay, is this code, given some template arguments, does it yield something valid? So, of course, for something such as 2 plus 2, there won't be any issues. Compiler checks it, and that works. And likewise, if you have something that doesn't depend on any kind of template argument, the compiler will directly check things, and if it's wrong, you'll get an error directly. Where it's interesting, it's when you are in templates, because when you are in templates, then the compiler can't directly say, okay, this works, this doesn't work. It has to wait until template instantiation to check if the thing is valid. And this allows us to do different things depending on the shape of our object. So for instance, we can check, does our object support being called with, say, integer argument and like the number of frames? And if so, let's call it like that. Else, if it requires inputs and outputs pointers like VST plugin, then we call it like that, etc., etc. And the idea is to come up with a library of such requirements. So named requirements are concepts, which allow to map the field of what is a media object. So once we have requirements, we can build concepts over this. So concepts are simply things that, well, will take requirements and turn them into a Boolean. So for instance, we can write a concept that check, okay, does this type T has a bar member function? So we can say, okay, for instance, if we want to check if our class struct has a prepare function that allows to, set up sample rate, that kind of thing, then we can do it. And if it doesn't have one, it's okay. We'll just call it like that, and it will still work, because if you didn't put one, it means that you didn't really need one. So we don't need inheritance to do this kind of thing. And a bit more advanced is that you can also use concepts to check the type of return value of an expression. So here we can say, okay, this concept means that we have type T whose bar function returns something which is either float, double, long double. So that is pretty useful. And then how do we use concepts in practice? How do we use concepts? So first you can put them in if const expr, and that allows us to do if, then else. And I thought that it would be nice to have it in switches too, but doesn't work so far, I think. And here you can just say, okay, if my struct has a foo, then we'll do this. Else, if it has a double foo, we'll do something else, etc. Second way is through template specialization. I'm yeah, I think it's specialization, the word, I'm never sure. And you can have a base template, which won't have anything, and then specialized templates, which will be instantiated if the type matches a concept. And they will take precedence over the generic one, the more generic one. So that's pretty useful to have one type for the general case and other types for a specialized case. And likewise, for functions. So one big thing in C++20 is that you can have auto as function argument, and it's equivalent to template type name t void f tt. And here we can just put either the concept name here, and this function will be called only if the type of x matches that concept. And there is this second syntax, which looks like the one for template arguments. So yeah, for us, it allows us to say, okay, is this processor something that works, for instance, per sample, per block? Is it a synth voice? Is it a video processor? That kind of thing. So here are some excerpts of concepts, for instance. So is it something that has programs? Is it something? Is this thing a MIDI message? Is this something that, well, is a port that works by sample? Yeah, this is a call, so please come and contribute new ideas of concepts, because the nice thing is that you don't need to include these concepts in your own code for your code to match those concepts. So it gives, of course, reassurance that it works. But unlike inheritance, it doesn't have any runtime cost, and it works for C structs and that kind of thing. So it's much, much better. And it's very similar to how people, for instance, are used to work in Haskell, with type classes. In Rust, well, Rust traits are not exactly the same as C++ concepts, but there are similarities. And it's something that works in other programming communities. So I encourage the C++ community to adapt these good ideas. Another good thing is coroutines. So coroutines are reasonable functions. So a very simple example, basically, they allow to do something like when this function is called here, the first time it's called, well, the first time we get our object, it will yield the first value and it will pause here. And then when we call it again, then it will go again through the loop and yield this value, etc., etc. So of course, it's very useful in asynchronous code, but in our case, it's useful for iterating. And iterating what? Iterating things with zero cost, more or less, which is, for instance, if we have a monoprocessor, we may want to create, let's say, 8 channels, because our host wants 8 channels of audio. And that means that we're going to have some stud vector somewhere if the host requests a dynamic number of channels. But I take zero cost very seriously. And when we have something which already handles multi-channel, I really don't want to pay the cost of putting it a single element in a stud vector, and I just want to have a struct with the object contained. So that leverages both concepts and coroutines. So our coroutine is here. So in the simple case where we know that we have a, let's say, polyphonic effect which is able to handle n channels, we just instantiate it once here. And here our effects will yield this value. And in the case where we have a monophonic processor, then here we will have a vector of effects, and we will just yield through the vector. So it's the most simple use of coroutines. And one thing is, at least with Clang, this is able to get optimized out. There is no dynamic allocation. For more complex cases, like there is way too much chance of dynamic allocation, so we have to be careful with that. But for simple things like this, yeah, in my experience, compilers are good enough to entirely optimize the whole coroutine stuff and just do like the loop is called directly at the calling site. But yeah, that's relying on compiler optimization. Yet that gives some nice code, and that's like, for instance, if you know a bit Java or C#, you know, you have this I collection things or collection library. Coroutines allow to have much more generic ways of defining collection, because you don't even need a collection type to have iteration on it. Another interesting example is template lambdas. So template lambdas is something that is just purely syntactic cigar. And okay, I know there is a lot of noise on that slide. There is more, I think, non-alphanumeric characters than alphanumeric. But so this is an interesting use of template lambdas. It's a function that will print the nth element of a tuple with n being known only at runtime. Because at compile time, of course, we can just do get n, but here we have a runtime value, and we want to lift that value from runtime to compile time. How do we do that with template lambdas? Well, it's very simple. No, kidding. We just have to create a sequence of index. So this is a type which will look like index sequence 0, 1, 2, 3, 4, 5, depending on the number of elements in the tuple. And then with this little trick, we can check, okay, are we at element 0, 1, 2, 3, 4, 5, 6? And this is done thanks to the fold expression here. And if that's the case, then we can print our number. This is just so that the Boolean operation works. And putting an OR here, in my experience, it ensures that Clang and GCC are able to compile that down to a jump table. So this really won't have any overhead over a switch, at least in the test I've done. So you can check the gold bolt link. And so why is it needed for? So, well, it really simplifies a lot of code. So before that, like we could do pretty much the same thing since C++11, but it used to be like stuff with recursive template instantiation, which took a lot of compile time and debug symbols for no good. So now everything can just fit in one single function. It also simplifies generic lambdas, so you don't have to use using the blah blah if you have a generic lambda anymore. And yeah, makes a lot of things simpler in the implementation. So be aware that this exists. And yeah. Third thing, which is super interesting in C++20, is generalized non-type template parameters. So NTTP is basically, you have std array, you can pass it an int as argument. So now in C++20, you can pass it literal types. So literal types are, let's say, types made of ints, floats, chars, stuff like that. So you can't have, for instance, a std string here yet, but you can have a lot of simple structures. For instance, here I have a struct domain with minimum and maximum. And we can say, okay, my template argument will be this domain. So it will be not a type, but a value, I insist. And then we can use that domain and return it from a function, and that will give us our compile time metadata that I talked about in the beginning of the talk, that used to be at runtime in all these parameter systems, and now we can put all the relevant information purely in the type of our objects. And with some niceties like designated initializers, we can even have not too bad of a syntax to say, okay, my control will go from -1 to 1. And here, the size of my control, well, there's nothing in it yet, so then we'll certainly put some float, and then it will rise to 4. But yeah, that allows zero overhead metadata on types, so that's not as good, I'd say, as user-defined attributes in C# and so, but, well, that's what we have. So for instance, this is how one will have a type to put random strings in template arguments. So you need this very simple static string method. We mark it constable to make sure that it is executed at compile time. And then here, well, we can just pass some string and it will construct this static string object. And then again, we can return it from some function and do what we want with it. So what we want to do is we want really our parameters just have the size of our parameters without having to go and take the address of some function somewhere. We just want to say we have this parameter. This is what is part of the meta object, the metadata of the object. This is what is part of the object, and perfectly segregate these things and put them where they belong. So yeah. So another thing which is pretty nice is constable. So I try to clear some misconception because constexfer is sometimes a bit misunderstood. And for instance, if you do something like this, you have this const_expr int add function. Even if you pass it constant argument, you have no guarantee that the compiler will run it at compile time. And indeed, if you check in my global link, you'll see that clang at 0 loads the value 2 in a register, loads the value 3 in a register, and calls add on it. So if we wanted until C++20 to say, okay, I want this to be computed at compile time, you'd have to put the variable const_expr2, not just the function, but you need to say, okay, this variable, it's a constant expression, I need it at compile time, and here okay, it will be computed directly, and which means that we can use it as a template argument, for instance. And in C++20, it's a bit better. Constable allows to make a slightly different trade-off, which is saying, okay, if I have compile time arguments, I want to make sure that this is computed entirely at compile time. And indeed, here you will also be able to check that this is directly computed, the value 5. And in counterpart, Constable says, okay, if we don't have compile time arguments, then compile error. There won't be any tries to make it work. So sometimes you may need const_expr, sometimes you may need constable, but I don't know if there isn't a better way to do that, but well. And finally, the big thing is boost PFR, which allows to do this. So actually, this is the most important thing, but it is here since C++17 and even before with hacks, but in a standard conforming way since C++17. Because it uses some techniques based on structural bindings, so and to read what are the members of a aggregate, and this allows to do something like, okay, for all field we want to read these fields. So I know that some of you may wonder about the compile time performance of this, so it's not too bad. It's logarithmic in terms of how many members there are in my struct. So, I mean, the idea is that one day, like the compiler already has this information, and ideally we should be able to get it directly at a constant cost. But well, that's what we have to play for the time being. And to give an example of more complex code that uses it, so for instance, in the pure data binding, so pure data, you know, is a graph system where you have objects and you connect them together. It's I'll make a demo of it afterwards. And here we have this function. We say, okay, if we got at runtime a message, so symbol is like a message name in the OOP sense. It's a very C-ish way of doing things. And if we have that, then we are going to first check, is it a float? And if it's a float, we are going to loop in all our types and look if one of our inputs have the same name than the message we got. We can see here that template lambdas are useful to just call static members directly. And if the stars align, then we'll just set the right value to the member inside our processor. And so that allows you to entirely go from the runtime system of pure data to our compile time safe class where all the parameters are just struct members. And so we don't have to bother with all the C API of pure data, which, well, sometimes is a bit hard to grok. So yeah, and the code is generated in terms of code gen that will just give a list of string comparisons, which is exactly what one would write in C when you get a message. At some point you have to check, okay, where does my message go? So yeah. So also when we combine boost.pfr with concepts, then we can do interesting things like filtering the fields of struct depending on the predicate. So for instance, if we want to get all the audio ports of audio inputs of my object, all the, let's say, media outputs, all the messages, we can do fun stuff like mapping controls to atomics, because so we can get the tuple, an equivalent tuple of our struct members, and say, okay, now with some metaprogramming library, we can say, okay, let's make an atomic version of this tuple. So this way, even if you don't write your code in a thread-safe way, the host will be able to ensure that things will be thread-safe, well, with some limits. So closing words. So yeah, structure-oriented declarative programming. I don't know, it's another possible acronym. Constable methods and non-type template parameters give something which is close to custom attributes. And if you fancy some Unicode fuckery, you can see something that really looks like custom attributes here, but it's not the same thing to do. Concepts and structure binding, it's getting us pretty close to reflection. And it gives us codes which doesn't depend on frameworks. So if you make an audio object and someone else in this room will just be able to copy paste this audio code and do fun stuff with it, it will still work in 20 years because it's just C++. It doesn't depend on some framework which may or may not be maintained, and won't have runtime errors due to runtime mismatches. And I'll just say that C++, we always say, okay, this is a bloated language, a lot of things, but when writing the library, it really looked like everything started to make sense and was coherent, and every time something was needed, it was there to use, and it gives something which is relatively coherent. So, of course, thanks committee members, and use C++20, it's neat. And my code has been tested with GC11, Clang 13, VS2022, so all released compilers. I'll just give a very quick demonstration of how, for instance, in Bitwig Studio. So here, for instance, here are some of my plugins. So, can I zoom Bitwig's UI? User interface. Okay. So here we have, for instance, simple processors written in that style, and we can see that they have, well, all the parameters. We can have the presets, which were listed in the example, if you remember. So, and if we have various funky types, for instance, if you have enums, things like that, then they can be reflected. And the code for this, it's always just this simple struct that I've shown. So yeah. So I think I'm good. So just go to the end. Yep. It's slow. It's super slow. It might be. Okay. So thanks for your attention. If you have any question, please ask. And if you think it's useful work, you can sponsor me on GitHub. Thanks.
Yeah, thank you. So did you end up using Boost actually in your library, or did you have to implement the structural binding for the members?
So in the library I just use Boost because I always use it in my project anyways. But if you want, you can just do it by hand. I can show the code actually. It's relatively straightforward.
And is there a limitation on the number of members?
So there is, if you download the library by default, it is built with 100 members pre-generated, and then they provide a Python script where you can just get as many as you want. So I haven't tested the actual limitations. I guess it's the compiler if it has a limitation on your number of overloads. But yeah, so far there is no technical limitation, just by default, it will run out at 100, and you have to know that you have to run the script. But the error messages will tell you that.
Thank you.
Do you think we'll be in a position in a few years' time where we're kind of fighting over which audio concepts we should be which audio concepts we should be following, and everyone will be fighting for which is the best concept?
Well, I think that's something, that makes sense. As for instance, I know if for instance, the REST standardization process, they have RFCs on GitHub where everyone discusses, and I think that's just the right way to do it. Like everyone should just go on GitHub and say, okay, this looks like a good concept, or this doesn't fit my use case. I think that's the best way to do it. But the nice thing is the people who write bindings can opt to check multiple different concepts, and if they have this concept and they can transform it in what they expect, if they have this other concept. So it's okay to have multiple competing concepts, and someone can still make something useful of it. Of course, it's more work for the person who writes bindings, but to give you like some numbers. So here, my library, how much line of code is it? It's 10,000 line of code, and there is Python binding, there is VST2, VST3, there is some QML interface generation, there is OSC. So per binding, it's like a couple thousand line of code, not even that. Like the Python binding, I think it's something like 200, 300 line of code. It's very, very short. If you look here, binding, up. I don't want to authenticate. What's that? No. Binding, Python. So this is the entirety of the Python binding. It's 138 lines of code. It just goes through all the inputs, outputs, and creates struct members through PyBind 11. So I mean, it's not that hard to add a check if it's concept A, let's do this. It's concept B, let's do that. And write wrappers that will dispatch to the correct concept.
Okay, one last question from the online community. There we have the question that if you have a filter, for example, where the coefficients of the filter are updated when, let's say, a cutoff parameter changes, so you have some kind of internal state of the filter of the system, how does your system apply to that when a more complex change needs to happen on a parameter change?
Well, right now, it will depend on basically what the host system does. Like, for instance, if it's a VST, what you get is basically, let's say in VST2, you get calls in your effect dispatch method, and you can just update them one by one, and you can do better than what the host allows you to do. And I don't know of any host which will have, for instance, some transactional way of behaving. I guess if that was the case, we could make it work, but I don't think there's a lot of systems which work like that. So synchronization, high-level synchronization, it will have to come from your own code, and you'll have to have some high-level parameter that you dispatch in your process block method into the right thing, if I think, yeah.